Nancy Rodriguez from the University of North Carolina at Chapel Hill, and she's going to talk on the global existence and qualitative behavior of one-dimensional solutions to a model for urban crime.
Thank you. Let me start off by thanking the organizers for this kind invitation and apologize one last time for stressing out everybody due to our miscommunication. But I'm very happy to be here. So here's an outline of my talk. I want to sort of start off with the introduction, discuss the model that we will be discussing, kind of motivate the reason for studying the global well-postedness of this system, talk a little bit about where the model comes from before I move on to actually stating our main results. And then I'll spend a little bit of time talking about the main ideas behind the proofs, just to give you a little taste of it without going too much into the details. And then I'll finish off with some numerical results to, either verify our proofs or sort of to show you examples of what the proofs or what the results actually are, and also to explore areas that we were not able to prove anything analytically about, but are still interesting and therefore leave some open questions in case anyone's interested. So I'm going to consider the following no-flux initial boundary value problem for this cross-diffusion system here. Okay. I will, again, explain everything where the model comes from in a second, so bear with me. But this was a model that was introduced by a group at UCLA, including Maria, who's here, for this parameter chi equal to 2 to describe the dynamics of urban crime. I will spend about 10 minutes discussing where this actually comes from so that you understand what all the terms mean. I will be working an omega, a bounded domain of R. Now, of course, the physical problem really is an R2, but it is a very difficult problem in 2 dimensions, so we were first able to just recently tackle the first dimensional problem. B1 and B2 are going to be prescribed suitably regular non-negative functions. And my first goal is going to be to discuss the existence of global classical solutions for any chi bigger than 0 and all suitably regular non-negative initial data. Okay? And then the second goal will be to study the qualitative behavior of solutions under appropriate assumptions of the asymptotic properties of B1 and B2. Okay. So where does this model come from? Hopefully, I won't bore you guys too much for the last 10 minutes because I know Maria talked about crime, so hopefully there will be some new information. If not, just bear with me. So this model was introduced to try to understand the spatial temporal dynamics of crime hotspots. These are regions where you have a high density of crime surrounded by areas of a lower density of crime. U is going to represent the density of criminal activities. For those of you who are familiar with this crime model, U is what we normally refer to as rho, and V is an attractiveness value, which actually provides how susceptible a location is to crime at a certain time. Okay? This system was actually derived from an agent-based model, which was basically the main assumption was that routine activity theory holds. It's just a theory that claims that opportunity is the main factor driving crime. So we don't have to worry about socioeconomic factors and so on and so forth. You can argue with this, but this is what what the model assumes. Okay? Also, within that realm, you assume and you model this repeat and near-repeat victimization effect. This is observed in real residential burglary data. It's just that if a house is burglarized, that house and its neighbors have a higher probability of being burglarized again for a short period of time. Okay? This kind of goes hand in hand with the broken window theory, basically that crime is self-exciting, for whatever reason. And so just so you get an idea of the agent-based model, and from that, I won't actually obviously do the derivation, but this will make it easier for you to understand how you go from the agent-based model to the actual continuum model. Let me just discuss the agent-based model using this schematic. Essentially, imagine that your city is a lattice, each node is a house, and then you have burglars. There's a probability that at a location where there's a burglar, that there will be a crime, and you assume that that's a Poisson process whose conditional expectation depends on the attractiveness value. The higher the attractiveness value, the higher the probability. And so it's a probability, right? So either you burglarize or you don't. If the burglar actually commits a burglary, you remove it from the grid, right? And if they don't, then you move it. And let me actually write down what this probability is, because it's important to determine how the continuum model comes from here. So this is the probability that you move, let me call it, from node S to node N1. And so if this is node S, this is N1, N2, N3, N4. This is going to be N1. It's going to be proportional to the attractiveness value. Okay? And actually, this assumption really is key to the type of model, continuum model that we get. It's very, very important. And so you move the criminal. It has to move. It doesn't have an option. You then increase the attractiveness value, as I said, because crime is self-exciting. And then because you're removing burglars, you increase you place sort of a certain number of criminals in your lattice. And that's it, really. These are the main assumptions. Okay, so here was our model again, and let me write it down. So that you remember it. Okay, so this is chi. Actually, this is minus chi. U over V, Bx, x. B2 of xt. Okay. So it is this assumption, actually, that leads to these two terms right here. But in particular, so let me write the original, just because we want to make sure that some of the theory at least covers the original model. Chi is actually equal to 2. Okay, so essentially this movement leads to some unconditional diffusion plus this bias movement where you're moving up gradients of the attractiveness value. And the difficult part here is that actually your speed actually depends on V. So the higher the attractiveness value, the slower you're moving, essentially. Why? Because if I'm already at a pretty good attractiveness value, I have less motivation to want to move to a slightly higher attractiveness value. But it ends up being a challenge because of this potential singularity here. Okay? And then the original value that was taken here, I'm just going to call it B bar, which is just going to be a positive constant. And then this is another positive constant, right? So this is the original model. But we want to sort of, in a way, generalize, study the generalized version. It is exact. I mean, if you make this assumption, and you take the limit, right? You have your lattice, and you take your limit as, these houses get closer and closer together, and delta t goes to 0. You take that limit, 2 is going to pop out. So it is because you made this assumption. Now you can choose another way that they move, and then you would end up with a different operator. But you cannot, the 2 comes from that. Okay, so just quickly, let's go over what each of these 2 terms represent. I already explained where these 2 terms come from. I said, if criminals commit a crime, then you remove them. So you end up with minus u times v, because this is the expected number of crimes, the product of u times v. B1 represents, again, the introduction of criminals in your system, which, again, in the original system was just a constant, but we want to generalize it. And then we have the near repeat victimization effect, actually, is this term right here. Because, again, if a crime occurs, this is the expected number of crimes. I'm increasing the attractiveness value. It's diffusing because we also have this near repeat victimization effect. Of course, it only happens for a certain amount of time, so you have some decay. And then B2 is just taken to be this base attractiveness value, okay? So that's what all of the terms represent. Okay, all right, so why is it interesting to study what I mentioned, the global existence and the qualitative properties of this model, right? Why do we care? Well, let me just briefly spend some time talking about, from the application perspective, the most interesting results, in my opinion, which I think it's enough motivation to make this a worthy problem of studying analytically. The first question, of course, was, you're trying to understand hotspots. Do they exist in this model? And it turns out, right, for the original model, you can see here that the only homogeneous steady state is given here. And you can do the typical analysis. You can perturb that steady state and try to understand how these perturbations grow or decay. And it turns out that you have a nice linear instability inequality that you can actually formulate based on the quantity A0 right here. And this is just an example of, given certain parameters, a case where you actually expect to have hotspots because the perturbations actually grow. And here, K star will give you the maximally growing mode in this case. And yes, the answer is yes, you actually have hotspots, and they can vary in size, depending, again, on the dominating mode. And also in the agent-based model, you observe hotspots. This is not what I want to focus on, but here's, I think, what is the thing that really motivates us to study this problem is what you can learn from it. And I think this is a very interesting result. If it helped provide some insight into this hotspot policing event. You can imagine, I don't know if Maria talked about it, but hotspot policing is what it sounds like, right? You have a hotspot, and you deploy your police force to that area, and some people believe that it works, and some people believe that it just moves it, right? So you can do a deeper analysis close to the bifurcation point, right? Of between the linear stability and instability, which I'm rewriting here, and simply do a weakly nonlinear analysis here. Let's not go into the details. But based on that, you know that basically the maximally growing mode will give you the base shape of the actual patterns. But the amplitude, then you can derive this amplitude equation. And it turns out that this constant C distinguishes between a subcritical and supercritical bifurcation, which then enables you to, you can analyze, you can try to simulate hotspot policing by introducing a damping field. And it turns out that in the subcritical case, right, so some parameters lead to a subcritical case, you can actually, you do hotspot policing and all of a sudden the hotspot is gone, you get rid of it and they never come back. But in the supercritical case, you can do hotspot policing, it disappears, and eventually it comes back, right? So I think, to me, this is a very nice example of what you can learn from, studying this PDE, that in some cases, hotspot policing works, and in some cases it doesn't, right? It might be difficult to fit the parameters, but at least you realize that at each city, you might want to try, what works in one place does not necessarily work in another place, right? So there is some interesting, useful insight that these types of systems can actually bring to the table. Okay. So that's some previous work. Let me just mention, a lot of work has been done in this model since it was introduced. So this is by no means a complete list, but let me just say that basically on the local and global well-postedness, we had local existence and uniqueness for the two-dimensional model in 2008. And then people have proved global existence, but only to modified systems. There has no one, from what I know, has been able to prove global existence in any dimension, actually, for the original model. People have actually also worked on, global bifurcation analysis. They've looked at symmetric and asymmetric spike solutions. They have added police. They have done many, many things, right? And this is by no means a complete list. I think the original paper has something like 200, citations by now. Okay. Okay. One last thing before I go to the results, and that is to talk about the connection to the Koiller-Siegel model, which I'm sure a lot of you guys are familiar with. But here's sort of the prototypical Koiller-Siegel model here. For chemotaxis, where now here U, for example, represents a density of bacteria or something, and V is a chemical. And so now the bacteria is moving up a gradient of the chemical. So if you consider the sensitivity function S is equal to 1, okay? Here, the cross-diffusion term and the linear production term actually has a destabilizing effect in multi-dimensions. It's known that this has global solutions when n is equal to 1, but then solutions might blow up in higher dimensions, right? We know that if the mass is suitably large, so in all of space, if it's bigger than 8 pi, we have finite time blow up. And if it's less than 8 pi, we have global existence. And then also it's known that blow up also can occur in higher dimensions, but now it's not based on the mass, but rather the L over n over 2 norm. Okay, so even with this nice sensitivity function where it's a constant, you have very, very rich behavior, right? Okay, so if you have a decaying sensitivity function, as I'm showing here, where let's say A and B and alpha are, A and B are positive constants, alpha is bigger than 1, then actually that provides a regularizing effect, okay? But we unfortunately have a logarithmic sensitivity function, right? Where actually we don't have this 1 that can help us out here. And so the sensitivity function that we have, which is chi over V, it's much more difficult to actually determine whether this actually has a regularizing effect. And in fact, for the Koiller-Siegel model, less is known. The picture is far from complete. There is proof for global well-postedness for a smallness condition, for chi being less than the square root over 2 over n, but that doesn't really help us. People have done slight extensions up to weaker conditions when n is equal to 2. For chi, again, less than 2. And then there has been some work done for larger values of chi, for n bigger than or equal to 2, only in certain cases for global weak solutions, which may become unbounded in finite time, okay? So it's definitely a challenging sensitivity function to work with again, it's what we have. And on top of that, we have this product here that adds even more challenge. Okay. All right. So that's enough of the background. Now let's talk about the main results. I'm going to assume that B1, B2 are non-negative functions that, again, are suitably regular. I'm also going to assume that the initial data is non-negative. And actually, V0, I'm assuming that it's strictly positive. And then the first result is that for any chi, our system here, CM, actually possesses global classical solutions. Okay? They live in the space, and they're less than 0. Or, sorry, bigger than 0. That would be bad. Okay, so that's the global existence. Notice that it's going to cover the original model. Now let me discuss the assumptions, the long-term behavior assumptions that I'm making on my functions B1 and B2. And I'm going to write them down because they're kind of important so that, you know, when I make the hypotheses, you actually know what I'm talking about. So for some cases, I'm going to assume long-time decay of B1. Notice the original model, that does not happen, right? B1 is a positive constant, so we certainly don't have this long-time decay. Okay, so if this is bounded, I'm going to call this H1. There is a weaker form, T plus 1. So if you have this go to 0 as t approaches infinity, I'll call this H1 prime. And then uniform positivity of B2. So we want this to be strictly bigger than 0. And then I might assume this. So let's assume that sometimes B2 stabilizes. Do I want it in L? Yeah. B2 xt. Okay, and this is H3. So we're assuming sometimes, again, I'm not going to assume, I'll tell you what I'm assuming, but this is a long-term decay of B1, right? This is the number of criminals that you're replacing, that you're introducing into your system. In some cases, we're also assuming that this is basically B2 is uniformly positive. And then in some cases that it stabilizes to the function that I called B to infinity, okay? Again, the original model satisfies H2 and H3, but not H1 or H1 prime, okay? Oh, what happened to? Okay, so we have global solutions, global classical solutions, but we also have more than that. We have boundedness for any chi bigger than 0 if we assume H2, which again the original model does satisfy. In fact, we have that there is a constant so that basically the number of criminals never exceeds that constant. And we do also have a lower bound and upper bound for the attractiveness value, okay? Furthermore, if we assume this long-time decay of B1, then the criminal density will go to 0, okay? Obviously, from the population, from the application perspective, they would be nice, but that's not going to happen, right? But so if we assume, obviously if we assume H1 or H1 prime, then we can show that the criminal density has to go to 0 in L infinity. Okay. The stability result is much more limited in the sense that now this is only true, or technically we can only prove it for chi less than this value here. Of course, it does include this guy here, chi is equal to 2. But now I'm assuming that H1 holds. So in this case, again, we do have that V is bounded. And also, V stabilizes to this function B infinity, which is the solution to the following boundary value problem here. Okay? Okay. So what are the main ideas for the proof of these guys? Well, for the global existence and the boundedness theorem, essentially for P, so between 0 and 1, and then Q positive, you have this functional here, which actually enjoys a nice entropy-like property that dissipates, okay? And that will help us get a space-time bound on basically UX and VX with some weights, where the weights actually depend on the solutions, okay? And then independently, because of the assumptions that we have here, you get a uniform lower bound for V. That's key to deal with this guy here. And then that helps with these two things. It helps get an LP plus 2 estimate for U for some P bigger than 0. And here is where the dimension comes into play, because in one dimension, these things then imply a uniform bound for Vx in LR for R bigger than 0. But this argument, everything goes out the window for higher dimensions. Also, in one dimension, this implies regularity for U in some Holder space. Okay, and so these are sort of the key estimates. The challenges are that basically as chi increases, and I'll show you the lemma so you'll be able to see it. Basically, P is reduced to a region close. It goes to 0, and Q goes to 1/2. Okay. So that's one of the challenges to deal with, and the other one is the coupling of U times V. For stability, you have, again, you again make use of the weighted, the norms on the weighted space, or UX and VX, for the same P and Q, but now the assumptions that I made, they don't guarantee the uniform positivity of V, which was much easier to prove if you actually assume H2. And so you have to pay the price by actually only being allowed to take chi in a suitable region, and then proving that U remains still suitably regular. And we can do that basically through a recursive procedure on LR, and then taking R to infinity. So it's much harder, and because we don't want to assume uniform positivity of B2, then you have to work a lot harder and pay the price by not being able to prove this for very large values of the parameter here, chi. Okay, so for global existence, we of course first start with the local existence. And again, under the assumptions that I made for B1 and B2, it's basically classical theory applied to tridiagonal cross-diffusion systems. You can easily determine that your solution will exist until t is equal to it's going to exist forever, or one of these three norms is going to blow up in finite time. So if we want to prove global existence, we just have to show that these guys remain bounded forever. Okay. Let me just discuss the basic estimates that are needed. And basically, we need a lower bound for the attractiveness value. If you don't assume anything, H1, H2, then basically you're going to have bounds that depend on time. And so, you need these assumptions to guarantee that the CT doesn't actually go to 0. Or for the upper bound for the criminal density bands, that the upper bound is not going to increase to infinity. And that's going to be true if either H1 or H2 hold. Okay? It's also important to get a bound on the product. Again, as I mentioned, it's sort of one of the challenges. And again, you need H1 and H2 to be able to show that these functions here are actually going to remain bounded. And you need an upper bound for the mass of the attractiveness value as well. Okay, so again, I mentioned that the fundamental analysis is of this functional here, u to the p, v to the q. Again, the key lemma will give us these L2 bounds on ux and bx with the solution-dependent weights. And this is going to be done for p between 0 and 1, and then q between 1 minus p. And then you want to get a spatial temporal bound for v in LR, which we happen to initially get for r less than 3. So this is really the key lemma that everything derives from. But here's where you can see that p here is bounded by 1 over chi squared. So as chi gets larger, p actually does shrink to 0. It's much harder to see that q goes to 1/2. But anyway, so these are the estimates that I promised, the weighted estimates for ux and bx. Okay, so then from that, you can get a superquadratic bound on the Lebesgue norm of u, again, for p being less than 1 over chi squared, which is then going to be sufficient to obtain a bound on the derivative of vx in LR in one dimension. Again, so here's a step where the dimension comes into place. But then this is enough to provide regularity for this inhomogeneous term. Again, in particular, key for the cross-diffusive term. And specifically, then you can prove Holder regularity in this case. Okay, so those estimates actually imply global extensibility of the local and time solution. And they also imply an upper and lower bound for u and v. The long-term decay of the solution then is really, all you have to do is take your equation, integrate it in time, do some integration by parts, and the assumption of B1, H1 actually then approves the claim. So u has to go to 0. Okay. For the stability results, you cannot rely on the global positivity of V because, again, I did not assume H2. And the problem is, again, that you have this singular taxis here that you're dividing by V. So you have to work a little bit harder to get the regularity of U. So to derive further bounds of V, we use its evolution equation and basically just use an LR testing procedure to estimate this crucial, basically you're just testing by BR, and then this basically is the difficult term to deal with. And to deal with it, we use this iterative setup where we basically choose arbitrarily large r where chi is sufficiently small. So that restricts our range for chi. This would be our iterative procedure, but let me not get into the details. I don't know that it would be very intuitive in any case. But you end up with this lemma. You have a bound for v q over p. And the idea is you want to, again, optimize this q over p. For the recursive argument, we have to set up a divergent sequence of Rk and basically show that we can show that if chi is sufficiently small, bounded by this constant here, and if h1 holds, then for any r, which is between 1 and Rk, this is actually bounded. But Rk is a divergent sequence, so basically we're done. And then with more work, a little bit more work, then you can show that V is actually regular, right? It's Holder continuous. And then then you can show that V actually converges. If you assume that B2 stabilizes in this sense, then V will actually converge to the solution to this boundary value problem, okay? Let me actually then show some numerical experiments that either help verify our results or explore regions. So for example, what if I don't have this long time decay of B1? What happens then? And I think it's more fun than to continue with the proofs. So the first thing that I want to discuss is sort of the exponential decay. Okay, so we were able to prove, that you have global solutions, and actually that if you assume, for example, B1, the solution actually of U decays to 0, but we didn't show that it actually decays exponentially. We didn't prove anything related to the rate. But we believe that it's exponential, and numerically we're able to verify that with multiple cases, but there is no rigorous proof yet. But so here is the case where you have B1 is e to the minus 2t and B2 is 1. So I'm satisfying essentially everything, H1, H2, and H3. And I'm plotting here the L infinity norm of U. Okay, so you can see that it increases and then eventually it decreases. And then here, just for kicks, I'm comparing it to the function some constant times e to the minus t. So you can see that the L infinity norm indeed does decay exponentially. But again, no proof. And this is for the case where chi is equal to 2. So that's one conjecture, that you have exponential convergence to 0. For the stability, remember I'm assuming H1 and H3. In this case, actually, I'm assuming H2 as well, not on purpose. But let me take B1 to be e to the minus t, and B2 to be this function here. And the main reason why I do this is because then you can very easily calculate the solution to that boundary value problem. Okay, this is actually the solution. And so then I can actually verify my stability result. And in fact, here is a convergence of V. So this is a steady state solution, and I'm comparing the steady state solution to this V infinity. And so in fact, you do see that it converges to this guy. And you see that U converges to 0, as it should, because I assumed H1. Okay, if this is really verifying my results. Okay, if B1 does not decay, okay, as hypothesized by the stability result, well then the results actually don't hold. So this is actually a sharp theorem. So if I change B1 to let's just say it's equal to 1, right? So B1 no longer holds. Then what we see numerically is that U and V do stabilize, but not necessarily to V infinity, okay? I don't know what it necessarily will stabilize to, okay? And U will not go to 0, okay? Which is actually more realistic. Okay. Also, to study a little bit more how sharp the results are, let's study the effects of a vanishing B2, okay? Because really, this kind of helped us deal with this logarithmic sensitivity function, but is it necessary? Well, for technical reasons it was, but in this case, let's try to explore it numerically. So basically, if I consider the case where B1 is just a constant and B2 vanishes, then independently of chi, when chi is small, U converges to 1 and V converges to B, okay? So this is what we see numerically. I haven't proved it. We don't know how to prove it yet. I really haven't spent much time thinking about it, but this is what we see numerically. As I mentioned, it seems to be independent of the initial condition and of the chemotaxis parameter for chi sufficiently small. So here's sort of one example. B1 is 2. B2 is actually decaying to 0, and chi is equal to 2. And actually, it's hard to see, but actually V is converging to 2 here and U to 1, which is what I just claimed right here. Okay? This is, of course, just one example, so but it seems to be independent of the initial condition and the parameter chi when it's small. Of course, when chi is larger, so look, when chi is small, you have u converging to 1, but when chi increases, in fact, you end up getting these spike solutions. The blue versus the red is just 2 different times to make sure that we actually have reached a steady state solution. Okay, and what about the effects of both vanishing B1 and B2? So here what we see is, again, the solution for various values of chi. So when chi is, and again, this is a steady state. So chi small, u goes to 0, v converges to something positive. But as chi increases, again, u still goes to 0, and it should, right? Because I'm assuming that H1 is satisfied, and that's what I proved. But V actually is converging to a non-constant steady state solution here. Okay, and the last thing that I want to explore is the effect of the chemotaxis on the solution growth. This is something that was observed also and studied rigorously in the Koiller-Siegel model, and we observed the same phenomena in the crime model, but we haven't developed any theory. So this would be an interesting problem to actually try to study for the crime model. But what you see here is actually the evolution of, again, the L-infinity norm of the criminal density, U, for different values of chi in a short period of time. Now, it's hard for you to see because it's not very clear what the maximum is, but this is like 5, and then 20, 40, and then this is like 70, 200, and like 450. So as chi increases, you can see that the L-infinity norm actually starts to get very large, but eventually, it always comes back down and settles down. So this is, you can sort of think of it as, a boundary layer. But of course, here chi is increasing. But if you think about it, it's not really, this is time, right? So it's like if I divide by chi, that's the smallness parameter, the 1 over chi. So this would be another interesting theory to develop, and I think maybe looking at the Koiller-Siegel literature is something that would be useful, and some of the techniques could be used there. Anyway, let me leave it at that, and thank my collaborator, Michael Winkler, and thank the NSF for its support, and thank you guys for your attention.